Welcome to this series of lectures on corrosion. Corrosion can be defined simply as oxidation of metals in certain environment. It is typically not beneficial, and we want to be suppressing corrosion. In this series of lectures, what we would be looking at is we'll begin by looking at the energetics of corrosion, which typically means we will look at the thermodynamics of corrosion. We will also look at rate-based approaches to corrosion because thermodynamics has its own limitation. We will look at the factors that affect the thermodynamics and the rates of corrosion. Finally, what is important is what are the typical methods that are used to suppress or prevent corrosion. These fall under the category of corrosion protection. So this is a very old field. Okay, this has been around for quite some time. In its oldest avatar, probably corrosion was relevant for suppressing corrosion in iron and steel application. Perhaps in later people looked at how to suppress uh, corrosion, let's say in bioimplants. For example, you may have an artificial hip. Okay, a hip replacement typically has certain alloys, and how do you suppress corrosion in such alloys? Or you may have dentures in your mouth. How do you suppress corrosion of metals that goes into dental fillings and so on? These are typical applications, but this perhaps was and probably is the biggest application of corrosion. How do you suppress corrosion in iron and steel? Um, but corrosion has evolved. To look at the way corrosion has evolved, we can look at um, the electrochemical applications under two broad categories. In one category, which I would probably call as electroanalytical system, that is the application centered around analytical systems, electroanalytical systems. This can be electrochemical sensors. These operate mostly in aqueous environment. So these can be biosensors and so on. And in fact, a human body has a lot of sensors, and all these things are electrochemical in nature. For example, tongue has a lot of electrochemical sensors, nose has electrochemical sensors, and these electrochemical sensors communicate with the brain. And this also involves a lot of electrochemistry. That is, the neural transduction, signal transduction, also involves a lot of electrochemistry. Um, um, these are one class of applications. And broadly, another class of applications can be categorized under electrochemical energy conversion and storage. These involves applications relevant to batteries, fuel cells, electrosynthesis. This can be very simple synthesis of um, compounds like hydrogen, oxygen, chlorine, and so on. And it can also expand to more complex um, electroorganic synthesis. And of course, a big application is the photoelectrochemical applications. Let's say photoelectrochemical splitting of water into H2 and O2. In all these applications, that is in all the electrochemical energy conversion and storage application, the condition is often harsher compared to conditions in certain biosensor applications. Here, you may have aqueous environment, but in mostly neutral pH. Um, but in these applications, the conditions um, is typically harsher, and it can be due to acidity of the solution. For example, in electrosynthesis, for example, when you look at oxygen evolution reaction, your electrocatalyst need to perform under fairly acidic condition. Okay, so corrosion of electrocatalyst under acidic condition is perhaps a grand challenge in electrocatalysis. And acidity is one of the main reason why the condition becomes harsh. In photocorrosion, you may be exposing the material to light. There can be electron hole excitation, which leads to certain types of corrosion. Photocorrosion, we may look at this in certain lectures later in this course. And of course, in batteries, um, the electrolyte is often non-aqueous. In lithium-ion battery, for example, you have um, other electrolytes which are not based on water, and the electrode electrolyte is unstable, and it leads to the formation of solid electrolyte interface and so on. So the message I'm trying to communicate is that these applications often have harsher condition, and corrosion has evolved to look at these harsher conditions compared to um, uh, the primary application of corrosion, which is based on iron and steel. So corrosion under modern avatars has been looking at these kinds of applications, including applications in nuclear engineering environment. This can also be very harsh conditions. Um, so um, typically, corrosion has evolved, especially in the modern avatars, under this umbrella. More broadly, it is categorized under material degradation. So, the main thing to understand is that despite it being an old field, it continues to be very relevant, and a lot of fundamental studies are being undertaken in this area so that a broad range of applications can be addressed. So, corrosion can also be looked at in a different way. It is often the case that electrochemistry is hidden from plain sight when you look at corrosion. What do you mean by that? So, when you look at electrochemistry, the presence of two electrodes is obvious, and these two electrodes are separated via um, electrolyte. Okay, so that is the typical electrochemical condition which you have often seen. But however, in the case of corrosion, this might not often be the case. For example, in the case of, let's say, what will be referred to as uniform or generalized corrosion, there is a surface which is getting corroded. Okay, there is no simple or obvious way to look at this material as having an anode or a cathode which is separated. So the role of electrochemistry in this case is not very clear. So because of these reasons, the connection between electrochemistry and corrosion was delayed. But later it was made, and we will look at corrosion from a fairly electrochemical viewpoint. In some other cases, the role of two electrodes can become more obvious compared to this scenario. So there can be an active material and uh, more noble material. This material tends to get corroded. We will look at this under galvanic corrosion. But even in this case, what is to be noted is that these two metals are shorted. Okay, so this is not the usual case in electrochemical systems, right? If you have, let's say, two electrodes, they are typically separated by an electrolyte interface, but that is not the case here. Okay, so these two material, one might be anodic and other might be cathodic, but they seem to be shorted. So how do you look at the corrosion from the point of electrochemistry when you have some such scenario? There are other instances, let's say crevice or pitting corrosion, um, where again, uh, as opposed to uniform or generalized corrosion, you may be able to identify slightly two kinds of regions within the same material, um, which is undergoing corrosion. We will look at all these things in subsequent lectures. So, as is typical of our lecture series, we start with energetics and thermodynamics of physicochemical phenomena. So, in corrosion, as I mentioned, so corrosion involves oxidation of metals. You have metal here in the form of a solid, um, oxidizing in typically dry air to form metal oxide. So when you look at this, you look at the free energy of oxidation. So only for gold, the free energy of oxidation is endothermic. So you can be assured that the corrosion of gold is non-spontaneous. But however, if you look at other metals, this oxidation is can be spontaneous. The delta G can be negative. So this is one class of material. This is another class of material wherein the delta G of oxidation, metal oxidation, is much more negative compared to this set. So if you look at the trends, what we have done is that chemically we have gone from more noble metals to less noble metals. To, gold, silver, and copper are in the same period of the periodic table. Uh, these metals are more noble compared to this, and their delta G is um, much less negative compared to this. Okay, so this is much more negative compared to these numbers here. So as opposed to these two classes of material, there is another class where the delta G of oxidation is much more negative than any of these metals. So broadly, we can look at corrosion under these three categories: corrosion of noble metals, corrosion of this class of materials, and this class of metals. So even though delta G of oxidation is negative for many metals, only alkali and alkaline earth metals readily react with dry air. Okay, so because this is because the corrosion rates are typically slow despite exothermicity, despite thermodynamics indicating these processes are spontaneous, corrosion rates are typically slow. So this is that is good. Okay, so in that manner, we can suppress corrosion to a good extent in many class of metals. So in addition to this, metals like aluminum, chromium, and titanium, um, despite having very negative delta G, they are resistant to corrosion because the surface of these metals form a metal oxide, uh, which prevents further corrosion. Okay, so there is a passive metal oxide film that is formed on the surface of these metals, which prevents further oxidation and corrosion of these metals. So it's good to look at the metals under different categories. So all these things are oxidation under dry air conditions. As opposed to dry air conditions, um, impurities significantly can affect the thermodynamics of corrosion. For example, if you look at hydrogen sulfide, this is not an uncommon impurity in oil and gas industries. The presence of hydrogen sulfide affects the delta G significantly. For example, if you look at silver oxidation under dry air condition, delta G was -5. As opposed to this delta G is -121. So this process is much more spontaneous compared to the oxidation of silver under dry air condition. You can again look at copper. Um, Sulfur dioxide is again not an uncommon impurity in oil and gas industry. The delta G is fairly negative compared to oxidation of copper under dry air condition. Um, this reaction is very important under marine um, conditions. So iron reacts with oxygen in the presence of chloride ion and protons, and the capacity of chloride ions to ligate iron is a significant pathway for corrosion of iron. This has to be suppressed under marine environment. So corrosion of iron under um, marine corrosion is an important field. We will look at these examples in as we progress along. And another case wherein chloride ion plays a big role in corrosion is that we just discussed that alumina forms a passive metal oxide film suppressing further corrosion. However, when you have chloride ion, this readily reacts with alumina, forming this component. So the passive metal oxide barrier to corrosion is broken in the presence of chloride ion. Why is this important? Because sometimes chlorine, um, there is NaCl, typical rock salt, mixed with certain solvents, is used as a de-icing agent. Okay, in Western countries where there is a lot of snow, you spread some salt and to melt the snow, and this chloride ion can react with alumina and dissolve that passive metal oxide layer. So we will look at all these cases as we progress. So the most important impurity is water, of course. So when we talk about presence of water, it is not necessary for the metal to be completely immersed in water. That might be the case in marine corrosion, but even just a thin film of water can play a big role and significantly affect the thermodynamics. The thermodynamics is affected in two ways. So here, the delta G of oxidation under dry air condition is shown. Here, the delta G under the presence of water is mentioned. In most cases, the delta G becomes much more negative. For example, for silver, it becomes from -5, it becomes -40. And for example, um, zinc, it becomes much more negative, and so on. Not only that, it the pH has a significant effect on the thermodynamics. So typically, corrosion is much more prevalent in acidic condition. So in acidic condition, pH is the value of pH is less. Therefore, delta G is more negative. So compared to corrosion in basic condition, the corrosion in acidic condition is much more severe. In the next lecture, we will look at um, this question why um, electrochemistry is more or less hidden in corrosion. So we will look at this under this title. Two electrodes on the same interface, how do they come together to give rise to corrosion? Thank you.